Good afternoon. This afternoon's discussion is going to center around motor design considerations when adding forced convection fluid cooling to the machine. I thought the best way to do that would be to actually discuss and describe the impact it would have on a particular motor. So I've taken the liberty of choosing one. It's a brushless permanent magnet motor with 3-phase on the stator winding. We're looking to deliver 200 kilowatts of output power, and at 25 RPM, that means roughly 80 Newton meters of torque to the shaft. We're looking to do this with 100% duty cycle, steady state operation. Further, I've constrained the design to be surface mounted rotor topology with an 8-pole rotor and a 24-slot stator. And physically, I've constrained the machine to be overall 210 millimeters in diameter. The lamination diameter is 170 with a 20 millimeter thickness on the housing. The overall length of the housing is 350 millimeters. The stack length takes up 200 of that millimeters. Each end winding is 40, and we have roughly clearance of 20 millimeter on either side, and the end plates are 15 millimeters thick. With regards to the air gap, the magnetic air gap is 3.5 millimeters due to the high rotor velocities. The rotor is actually contained within a non-magnetic shell. That shell is 1.5 millimeters. And that means that the physical air gap is 2 millimeters. The motor is supported by 40 millimeter diameter shafts, which is 400 millimeters long. As you know, materials are a very dominant part of the machine response, so I figured we would talk about that. We're going to use round copper wire with American gauge. We'll use full or half size depending on the design, final design here. Both the rotor lamination, stator lamination, and the rotor back iron are M1929 gauge. To use these in a simulation, we need to define the first quadrant BH loop data and also any core loss data that we have with a function of the frequency and the excitation. The rotor sleeve is going to be made up of a carbon peak weave. Shaft is made of 304 stainless. The housing and the end plates are both all made out of aluminum. And I've chosen a fairly standard epoxy here with 0.176 watts per meter per degree C. Regarding the permanent magnets, they're defined by the second quadrant BH loop data. And I've chosen to assess, and we'll review 2 different machines, one neodymium iron boron class, which is a 34 megagauss Ørsted energy product, also a samarium cobalt magnet with the 28 megagauss Ørsted energy product. With regards to the forced convection and the duct cooling that we're going to add, this takes on the form of a water jacket in the housing. There are going to be 24 channels. Each of them are 10 by 15 millimeters in cross section. They'll be equally spaced around the circumference, forming parallel paths with the fluid passing from the left of the machine to the right. Each of the channels will be full of ethylene glycol water mix, 50-50. The inlet temperature is going to be 20 degrees C. And then we're going to explore 3 different flow rates, 0.5, 1.5, and 2.5 liters per second. Now, physical prototyping certainly is a valid way of assessing one's design or iteration in design. And it can certainly be used to develop an optimum motor. The problem with physical prototyping is that each iteration and design is expensive to fabricate, it's expensive to build, it's expensive to set up and test, and each of these iterations takes time. So in an overall elapsed time for a design can be months. So we're proposing an alternative today in the form of MotorSolve simulation software. It's an application-specific software for assessing the performance of motors. And MotorSolve takes advantage of electromagnetic performance criteria by simulating 2D magnetic finite elements. It also then simulates thermal performance using 3D thermal finite elements. And by doing this, we can change the overall elapsed time from several days, weeks, or months down to a few hours. So as I assessed the motor that we're going to review, I allowed myself the flexibility to review the magnet thickness, the magnet width, and then regarding the stator, I allowed myself the flexibility to review the slot opening width, the tooth tip thickness, the slot depth, and the tooth width. Using MotorSolve's stator winding interface, we have the ability to assess the nature of the balance of a particular winding layout. And that is referenceable to the number of poles, number of phases, and the number of slots. Based on those inputs, the product has a layout reference which allows you to describe and see a balanced layout and the choice of several if that exists. And what you can do is assess whether or not you have a preference for a particular layout. If your configuration doesn't have an automatic layout, it would look like this. There are some scenarios where you might actually want to manually use your own layout. I chose to use the default. So our first criterion for looking at the performance of this motor is going to be, can we put enough copper into the slots? So we're going to review things as we set up the motor. We're going to review the slot fill, which we're not going to allow to be higher than 40%. We're going to assess a number of turns for a wide range of wire gauges. We're going to try and make sure that our current density does not exceed 10 amps per square millimeter. And what's handy is the interface allows us to assess this on the fly. So here you can see that I have chosen a wire gauge, a number of strands in hand, and a series of turns here. You have a reference for the fact that my coil fill is 40%, and you can see the overall resulting impedance. So now that's all well and good if I can put copper in, but I also need to be able to deliver the output power. Can I deliver the 200 kilowatts? Or better stated, can I deliver the 80 Newton meters at 25,000 RPM? And so MotorSolve has a wide range of experiments that we can choose from to assess the physics of the machine, and I'm going to choose a couple of them for this particular criterion. In particular, I'm going to look at and choose the torque speed curve. So I ran and run the torque speed curve. Here's a typical output. And indeed, you can see that the machine was able to deliver 80 Newton meters for well beyond my criterion of 25,000 RPM. Additional to that, I wanted to double check things and run a motion analysis test. And so I ran that, and you can see here that I had my 80 Newton meters, and I've delivered over 200 kilowatts for my machine. Now, the motion analysis is very important because it's the way that we can use the finite elements to calculate accurate losses. And I'll go into that in a little bit more in depth later on here, but you can see here that we're tabulating total losses to the winding, and then there's a broad section here for the losses within the lamination for both the stator and the rotor. And then note also that we have computed losses from the magnets. As the rotor is rotating very fast, the magnets will have induced eddy currents in them. So in an effort to actually keep things as cool as possible, I'm also going to try and constrain the flux in the active components and keep the flux density below 1.6 Tesla. That's 16,000 Gauss. I want to try and do that for the stator teeth, the stator back iron, as well as the rotor back iron. And so using a different test within MotorSolve, I can actually assess the local distribution of the flux density. So here's a typical plot of the flux density in a machine, and you can see here that I've normalized the scale from 0 to 1.6 Tesla. I'm plotting both the flux lines and the color shades to give a good representation of things. And you can see that there are no deep red spots, meaning that I have succeeded in keeping the flux density below 1.6. Additionally, if I zoom in, I get to see a little bit more detail associated with where I have high density. And then if I actually go in and use what we call field probes, I can assess more readily and see that in the tip of the tooth, I've got a little over 1.5 Tesla. And in my tooth base here, I've got a little over 1.4, but both well below the 1.6 that I want to set as the high criterion. Additionally, I have a criterion for the machine which says that I don't want a lot of cogging torque. In fact, I'd like it to be less than 1% of rated torque, meaning less than 0.8 Newton meters. So relying on my MotorSolve experiment list, I can also run a cogging torque test. And that allows me to review and see that I have less than 0.6 Newton meters, well under my criterion. And this allows me to feel comfortable with this particular constraint. And I have one last criterion for the machine magnetically, and that is my back EMF constant. And I want to be able to generate at least 19 volts. So the typical output. As a multifaceted design criteria, I have a list of things that I'm looking for. And so we have decided to make sure and maintain that we have slot fill. Current density is under 10 amps per square millimeter. Deliver that advanced angle of 40 to keep the flux work in the back EMF constraints. This is a snapshot of the optimum design. Here for the rotor that I had flexibility to change, so we have a thickness of 10 millimeters and a width of 25. For my stator, my 4 parameters, I have a slot depth of 30 millimeters. My slot opening is 2.25. My tip thickness is 2, and my tooth width is 7.5. The ending design had 8 strands in hand with 2 turns of number 10 wire in my conductor slots. The end winding itself had an overall extent of 40 millimeters. Here's a physical summary showing the mass of each of the components. You can see here that my magnet, both the rotor and the core, We're both around 3.5 kilograms. Shaft is 4. I've got 5.5 kilograms of wire, almost 15 kilograms of lamination. The total mass of the machine is 41 kilograms, or roughly 90 pounds. Up to this point, we have done all of our experiments at 20 degrees C. What's interesting is to try and assess what happens to the motor when it's driven at this 100% duty cycle for steady state operation. And how does the heat, all of the losses, change and impact the material properties and the overall performance of the motor? So now we're going to go into phase 2 of the discussion, and we're going to talk about coupled co-simulation in MotorSolve between our 2D electromagnetics and our 3D thermal physics. So before we far into it, I want to make sure that we understand that the losses are computed as part of post-processing. And so there are 3 basic components of losses in the machine, electric anyway. We have I squared R loss. We have eddy currents, which will be induced in the magnet, and these will primarily be due to the rotation. So these are motion-induced eddies. There will be some induced currents based on some dispersion. And then the laminations have losses, and these are based on adjustment of the finite elements. And those B fields are then mapped to the core losses in the database for any given material property. In this case here, for both the rotor back iron and the stator lamb. So that being said, we're going to do coupling for electromagnetics and thermal, and it looks a little bit like this. We're going to have the first consider magnetic simulation, a time transient simulation which extends several electrical cycles so that we have steady state operation, and then we extract RMS losses from each of the components. Those losses were described in the previous slide, and they have 3 different contexts. Those losses then are mapped as inputs to the thermal simulation, and the thermal simulation runs and gives us the corresponding temperatures. In iteration 2, those temperatures are used to modify the material properties for all the components. Then new losses are computed, and then we run a second thermal simulation to get temperatures based on a prorated profile of losses. And what I mean by prorated is that we use the losses from iteration 1 to start and the losses from iteration 2 to finish, and we interpolate in between so that we have an accurate representation of things. Furthermore, as we assess the thermal simulation, we have to actually describe what sort of excitation we want to have. And in the case of simplicity, I have described this duty cycle to be 100% rated torque at 100% rated speed for a full 60 minutes. I can add any number of intervals that I want into this definition of the interval here, and I can change the duration and the rated torque and such and speed to prescribe how that machine is going to function. But in this particular case, for simplicity, I have chosen to just turn it on and leave it on. Now we want to see how that responds. So we're going to go back to our experiment list, and we're going to run a temperature experiment. And you can see the result here for the neodymium iron boron magnet motor. And close inspection of this shows that the stator would likely have melted. It's a little over 400 degrees C. The magnet is over 350. Likewise, when I simulate and review the samarium cobalt, the profile is basically the same. The samarium cobalt magnet motor is slightly cooler, but basically the machine is going to be inoperable if we try and run it with 100% duty cycle without any sort of cooling. So that segues into the fact that we're going to add cooling. We're going to add axial flow duct cooling, more commonly known as a water jacket. And you can see here the interface that allows you to enter the parameters describing that series of ducts into the housing. As a summary, you can see that we have chosen 24 channels with a cross-section of 10 by 15 millimeters. All of the channels are connected as parallel paths to one another. The fluid is passing from left to right. And we're using a mix of ethylene glycol and water, 50% of each. We're going to induce 3 different flow rates and see what happens. And we're going to ensure that the inlet temperature is 20 degrees C. And as we move on to the overall simulation, it's important to note here that the heat transfer coefficients for any of the thermal simulations are automatically computed as part of the interface. So just as a summary, we have channels in the housing that are going from left to right of the motor, and they're equally dispersed around the circumference of the machine. And now let's go back to our list of experiments and let's look at the profile of the losses as a function of time due to our coupled simulation runs. So here you can see the losses associated with the end winding, and this would be the 20 degrees C losses from the first simulation. You can see here that each of the water jacket flow rates has a different result. Showing this is how are they for the 3 flow rates that we described, and you can see that after 60 minutes all 3 have stabilized. This one is around 150 degrees C, 130, 20. As I've got analogous 3 simulations, and as well as the coil. And now there's additional capability and technology in the product which allows us to look at the temperature a little more closely. And that is, we're going to look at the temperature on the components as a function of time and throughout this simulation. So we're starting with everything at ambient, which was defined as 20. As I step through time in 5-minute increments, you can see the distribution of the temperature change in all the components. And you can clearly see things heating up. For reference, this is the 2.5 liter per second design And additional technology exists for us to review more closely and to see with probes what the temperature is in localized places. Here you can see the end winding was around 103. Here you can see that the magnet, in this case, was around 130 in that location, and then the housing itself was around 46.7. Now, I have taken care to review both neodymium and ceramic cobalt motors, and so the next series of graphs are going to plot them one against another. And so here we have the magnets of the temperatures of the magnets as a function of time, and I've plotted them for the slowest flow rate, the 0.5 liters per second flow rate. And you can see that there's a difference in the samarium cobalt and neodymium based motors. The samarium cobalt magnet motor, is cooler by 9 degrees. Likewise, if I change to the middle or the second flow rate, which is 1.5 liters per second, I can see that the temperatures are different by 5.5 degrees C. If I go all the way up to the 2.5, I can see that there's only a 4 degrees difference. But this is instructive as it shows us how these two machines changed. Now, why do we care whether or not our magnets have any problem or vulnerability to temperature? Well, it has to do with our concern for losing the energy, irreversible loss in the energy. So I apologize, but I do have to show an equation or a relationship here for ferromagnetism. I've shown both MKS and CGS. Yeah, in these relationships, it's important to note that I'm talking about the flux density within a volume, and it's a vectorial addition of two things impacting a particular volume. Those would be an applied field H and the volume's response to that applied field. And these do not need to be in the same direction, and in fact often aren't for permanent magnets. However, it's important to note that this vector sum does hold. So now let's look at a typical neodymium magnet. In this case here, I'm looking at a vacuum schmelz 667HR material. And to demonstrate my point, we're going to concentrate on the furthest right curve here, which is the data for 210 degrees C. Now, even though my magnets are cooler than that, and I won't have any issue because of that, I want to just describe the point of why we care and why we have vulnerability to this. So, for instance, if my magnet has an operating point described by this middle red line, and it intersects my magnetization curve at this red dot, then because of my previous vectorial algebra, I have this point corresponding to my B curve. And those two quantities plus the corresponding H will be vectorial summed. Now, if I apply a field anti-parallel, then I get a second load line curve, and the operating point of the magnetization changes from this first red line dot to this red dot. The corresponding red dot for the B curve jumps down here. You can see that I've gone below the knee. And in both instances, I've projected back with a dashed line back to a new remnants. And you can see that I have irreversibly lost magnetization. And in fact, if I take this applied field off, I will recoil along these lines to my new spots, the orange dots one along the load line and the other one associated with the corresponding H. And you can see that I have lost energy, lost part of the initial magnetization, and that will not be returned to us. So this is one of our concerns as we try and assess the temperature of a machine. Now, as I said, we're operating, the highest temperature was around 160 degrees C. At 160 degrees C, there is no knee in the second quadrant for the B, and so our vulnerability with any standard load lines is not high. To underscore the fact that I lose flux, corresponding to a standard loss of magnetization, which is roughly 11% per 100 degrees C, I've plotted the flux density in the magnets for the neodymium, and I go on from 0 to 1.2 Tesla, and you can see here that I've got some fairly high flux density. If I go to my 0.5 liter per second case, where my magnets are the hottest, you can see that I've lost magnetization here. If I drop to the middle, 1.5 liter per second, you can see the distribution of flux changes again. As well as if I go to my coolest operating, you can see that it's different as well. None of these actually are in danger of being irreversible, but they do show a clear indication of the loss of flux. Just for reference, that's what we started with at 20. So now, if we look at the analogous material for or the response for samarium cobalt, again, I've chosen vacuum schmelz 225 HR just for reference sake. Again, if I have a load line that impacts the magnetization curve, and I drop down a parallel line or a vertical line, I get an operating point for my B. All three of these quantities, the B, the M, and the H, will vectorially add. If I then add an additional excitation, anti-parallel, I get a new load line here. That corresponds to a second red dot. I get a corresponding second red dot for my B. And note here that there is no knee at all, and so we're completely free of any vulnerability with the samarium cobalt. So now, with regards to magnet stability, although the strength of each of the magnets has been reduced or weakened by the increase in temperatures, all of those changes are actually reversible. If the machine is to be cooled off, flux densities would revert to their originals. As a function of the three different cooling representations, we have anywhere from an 11% to a 16% loss of strength in the magnets for neodymium, and only 3 to 4% loss for the samarium cobalts. With our assessment of the second quadrant, we can assure ourselves that while we are using those three configurations, that's above the knee, and we don't. So now let's switch gears. Winding, comparing the winding for my neodymium-based motor and my samarium cobalt-based motor. In this case here, again, I'm plotting 0.5 liters per second. You can see the profiles are basically identical. Overall, there's a 3% difference, a 3 degrees difference after an hour. If I switch to the 1.5 liter per second, again, they look very, very similar, and I have less than a degree difference. I go to the 2.5. There's almost no change in the response of the machine from the standpoint of the temperatures and the winding. So let's assess what that means with regards to how things change for the conductors. So we know, in general, I get 40 degrees increase in temperature with 100 degree in resistance, sorry, with 100 degree temperature rise. And using the fact that our initial resistance, line resistance, was 4 milliohms, I can compute at 120 degrees C, which is the state I have with 2.5 liter per second forced cooling. I've got 5.4 milliohms, which is indeed my 40% change. So there's additional concern that we have. And I've plotted the temperature lines at 120 and 135 and 160 on a standard lifetime insulation curve that I've gotten from IEEE. And we're not going to pay too much attention to our middle line here. We're going to concentrate on our extremes. So for 160 degrees, you can see that it intersects each of the 4 classes of insulation where I've put a green dot. For 120 degrees C, you can see that I've got intersecting curves and dots associated with those intersections. And we're going to scrutinize each of those 8 intersecting points. So let's do the 160 degree line first. This corresponds again to the 0.5 liter per second cooling configuration. And even though the magnets might be sound, let's look at what happens to our different classes of insulation. For class A, we have a lifetime of only 500 hours. That's only 21 days. That's less than a month. That typically would not be suitable for the operation of a motor. Likewise with class B, it's 2,800 hours, a little over 100 days, not even half a year. If I look at class F, we have 16,000 hours, just under 2 years of overall operation. That likely would still be too short for any sort of warranty and any sort of quality control that you might have in your product. Class H is 70,000 hours, which is 8 years. Depending on the price and the range of the motor that you're designing, it's likely this would not be suitable either. Well, let's scrutinize and look at the same 4 dots for 120 degrees C. Class A is 7,000 hours, a little less than a year. Class B is 40,000 hours, 4.5 years. Class F is 260,000 hours, which is roughly 30 years. And Class H is 1.2 million hours, or 137 years. So very clearly, the temperature from our winding is going to dictate the lifetime of the motor. And we need to be careful and scrutinize based on our specification and such to pick the cooling and then also my class of insulation. So now I just want to clarify, I have run multiple designs to come up with the optimum overall layout of things, and then I ran 5 separate neodymium simulations, including the 20 degrees C, including the no cooling one, which went up to over 400 degrees. And then I've tabulated all of the typical data you might see in a nameplate, but I also have the losses and such for us to review. And I think it's important to note here that, in fact, the only thing that we get right at 20 degrees C is the losses in the magnets. And so we can predict there's going to be roughly 160 to 170 watts of loss due to the magnets rotating at 25,000 RPM. Everything else that we can see in this table shows us that, in fact, we can't rely on a 20-degree simulation, and we have to do a multi-physics co-simulation between magnetics and thermal so that we know the performance as a function of the co-simulation and reference points. Here's the same graph or table, sorry, for our samarium cobalt motors. Again, the only thing that looks like we can do at 20 degrees C soundly is the simulation of the magnet losses themselves at 300 watts. Everything else really depends on the co-simulation. We need to know the temperature of the components, we need to know the materials, and we need to know what cooling. So now let's compare for a moment. At 20 degrees C, it's very clear that the neodymium shows as a better performer. However, because we know that no motor actually operates at that temperature, it's important to go beyond that. And if we scrutinize all of the simulations for the magnets in each of the three cooling configurations, half, 1.5, and 2.5 liters per second, we see that the samarium cobalt actually is equivalent in performance to the neodymium, even though the neodymium starts off with a lot more flux density. And that's because of the flux loss that we showed with the shade plots. Now we have design success. We have achieved what we wanted to, which is 200 kilowatts, which maps into 80 Newton meters at 25,000 RPM. We've achieved that with a brushless permanent magnet motor, which is 3-phase. It's operating at 100% duty cycle within a package size of 210 millimeter diameter, 350 millimeter long. We have very clearly shown that forced convection cooling is absolutely required. We have shown that the water jacket successfully removes the heat, and I have shown some preliminary heat transfer coefficients here, but this is typically how you would reference the fact that we're taking all this heat out. So you have, with 0.5 liter per second, you have roughly 5,000 watts per square meter per degree C. And on the other end, we have 2.5 liters per second mapping to 20,000 watts per meter squared per degree C. And all three of these values are significantly different than the natural convection number for this quantity, which would be around 10. So this is the reason why the machine cools and why the components don't go up into the 400 C range. It's my opinion that the 2.5 liter per second design is the optimum solution. It certainly is the most conservative and will allow us to have the most flexibility regarding the installation and such. As we look at the magnets a little bit more in depth, we see that the samarium cobalt magnet actually led to a cooler overall motor by not much, a couple of degrees. We saw 9 at 0.5. At the 2.5, it was less than 5 degrees, but it would run cooler. And then as we approach and look at the appropriate class of insulation, it's really going to depend on the specification you have, but you can see that in this case here, class F would be a minimum, in my opinion, for the 2.5 liter per second configuration, and that would give you a 30-year lifetime.